The next topic dealing with inferences from two samples deals with the means. So in section 9.1, we dealt with proportions. And as we can see, the formulas are fairly similar to the formulas we've seen with one sample. The difference is they are a little bit more complicated, and it makes a perfect sense for them to be because we are dealing with two samples. And it's important to see again when you do the test statistic, if you look at the numerator, P1 minus P2 goes to 0 because it comes from the choice of H0. So we have the test statistic that is there, confidence interval, and when we calculate the confidence interval, we use a different formula. By that I mean we use P bar, Q bar for test statistic, but we use P1 hat and Q1 hat, and therefore the result for the confidence interval may be slightly different. So having said that, let's go to the new stuff. So the synopsis of what we want to cover, we are dealing with two means. So we're going to use sample data from two independent samples to test hypothesis made about two population means to construct confidence interval estimate of the difference between two population means. Two samples must be independent. The sample values from one population are not related or somehow naturally paired or matched with the sample values from the other population are considered independent. In the case of a dependent, when two samples are dependent or consist of matched pairs, if the sample values are somehow matched, where the matching is based on some inherent relationship, for example, before and after giving medication to some subjects. The objective is to deal with the hypothesis testing, construct the hypothesis test of a claim about two independent population means, and coming up with the confidence interval, construct the confidence interval estimate of the difference between two independent population means.
The two samples are independent. 2. Both samples are simple random samples. 3. Either or both of these conditions are satisfied. The two sample sizes are both large within N1 is greater than 30 and N2 is also greater than 30.
We are basically dealing with normal distribution, or N is large. How large? N was large previously, now N1 and N2 both must be large. How large? Larger than 30. Now, so we have that as far as the requirement is concerned. So we have sample 1, sample 2, and the population, mu1 equals mu2, the difference is not significant. And if we end up with rejecting H0, then it becomes significant. And that's really the idea. What's happening now, either sigma 1 and sigma 2 are known, in which case we use the z-test, or they are unknown, which we are going to use the t-test. We're going to look at those also in a moment. For now, remember x bar plus minus e. Now x1 bar minus x2 bar plus minus e. So they are the same conceptually. So you calculate the e. If you recall, e was for one sample, z alpha over 2 square root of sigma over square root of n. Sigma over square root of n. Now it's sigma 1 squared over n1 plus sigma 2 squared over n sub 2, because the variances add up in that sense. And it gives result of test statistic as follows. And notice again, if you look at the test statistic, this comes from H0 and it goes to 0. x1 bar minus x2 bar over the square root of sigma 1 squared over n1 plus sigma 2 squared over n sub 2. What I want you to notice is this. If you look at the value of e, I hope you see how similar it is to the denominator here. Why am I mentioning this? Because when you want to calculate your confidence interval, you need to calculate e. But to calculate e, what you need? To calculate the confidence interval, you need x1 bar minus x2 bar. This is the same as this numerator. So it makes your calculation easy. And the e is the same as the denominator times z. So if you have kept your calculation, the confidence interval can be calculated extremely fast. And now, if you want to use a TI, the z-test and the z-interval is explained how you can do that for using stat, test, two sample z-test, enter the information and choose the tail. Or you can do the interval accordingly.
A survey found that the average hotel room rate in an upscale area is $88.42, and the average room rate in a downtown area is $80.61. Each sample contained 50 hotels. Assume that the standard deviations of the populations are $5.62 and $4.83, respectively. At alpha equals 0.05, can it be concluded that there is a significant difference in the rates?
When we read this question, we got to be able to write the given. So we have upscale as one group. The average for upscale is 88.42. This is X1 bar. Each one has the same size. N sub 1 equals N sub 2 equals 50. So that's the same for both. And sigma 1 is 5.62. This is sigma 1. Downtown area, the average X sub 2 bar is 80.61. N sub 2 is the same as 50, and this is sigma 2. Alpha is 0.05. It's a SRS, simple random sample. We are dealing with two different populations or samples, if you will. Upscale X1 bar and N sub 1 and sigma 1. And the same thing downtown, we have those three. When we write H0, obviously mu1 equals mu2, that would be H0. But what about H1? Let's read the question. At alpha of 0.05, can it be concluded that there is a significant difference? It doesn't say less than or greater than. So it's not equal. Can it be concluded? And that is the conclusion they're asking us, so that is the claim. So H0, mu1 equals mu2. H1, mu1 is not equal to mu2. That is the claim, and it makes it a true tail test. So with that being the case, you need to calculate the test statistic at top right. We have the formula, we plug in. Now this is what I want you to pay attention to. The numerator, you will need it for confidence interval. Remember what we are doing here. We are using CV, the critical value method known as traditional method. So you're going to need the numerator for the confidence interval. So you want to make a note of that number. You need the denominator for that also when you calculate the E. So you would want to make a note of that. So calculation of confidence interval becomes extremely fast and easy. So the test statistic here that you calculate, if you're careful, it will help you with confidence interval also. And so this gives us 745. Critical value comes from the choice of alpha. Alpha is 0.05. This is a two-tailed test. So plus minus 1.96. We do the drawing, and 7.45 is way into the rejection region. 7.45 is way into the rejection region. So you are going to reject H0. When we reject H0, what happens? Then we look at step 1. You're rejecting H0. That means you, in essence, you're not rejecting H1. So you're not rejecting the claim is true. And you do the right.
Decision A, reject H0. B, the claim is true. C, there is enough evidence to support the claim that the means are not equal. Hence, there is a significant difference in the rates.
Of course, if we were to use a calculator, this is what we end up with. And remember what the calculator gives you. The calculator gives you the p-value. So you're going to be able to do the test statistic on your own if you're asked. So take a look at the p-value here. And the p-value is extremely small, 9.238615 times 10 to the power of negative 14, practically zero. And remember, beyond 3.5 or 4.0, if you look at the table, it's considered 0.0001. So that was the critical value or the traditional method. As far as the confidence interval is concerned, as I mentioned, look at the top right, the formulas. We need x1 bar minus x2 bar. It was the numerator of our test statistic. We need the E. E is the product of the denominator of that and Z. Z from the previous page was 1.96. And the square root of sigma 1 squared over n1 plus sigma 2 squared over n2, we should have that from the previous page. This, you should know the number, you should know the answer from the test statistic to make your life easy for the sake of calculation. I wouldn't recalculate this. I would use the test statistic from the previous page. All right, so having said that, this is another one. This part is the numerator of test statistic. You want to keep that. And so plus minus, and it gives us the following. That means mu1 is between the two numbers 5.76 and 9.86. Clearly doesn't contain 0. Therefore, you're going to reject H0. That should give you, and it does give you, the same result. So pay attention to the fact mu1 minus mu2 is between two positive numbers. What does it really tell you? In essence, it says mu1 is larger than mu2. If both of them are negative, it says mu1 is less than mu2. And if one of them is negative, one of them is positive, that means mu1 equals mu2, or mu1 minus mu2 equals mu. By the way, having said that, H0 of mu1 minus mu2 equals 0 is the same as mu1 equals mu2. It means the same thing.
Interpretation. The confidence interval limits do not contain 0. Therefore, there is a significant difference between the two average rates. The confidence interval indicates that the value of mu1 is greater than the value of mu2. So there seems to be sufficient evidence to support the claim that there is a significant difference in the rates.
We can input the data and we can calculate the confidence interval using a calculator as follows, giving us the same result with more decimals. By the way, if I'm calculating the E, I would put more decimals. Let's look at what happens when sigma 1 and sigma 2 are not given. We are dealing with the same situation as far as the two samples being independent, as far as dealing with simple random sample, SRS, in both cases. And we either have population which is normally distributed for both samples, or N is large. By that we mean N sub 1 is large and N sub 2 is large. How large is large? Larger than 30. What happens when sigma 1 and sigma 2 are unknown? By the way, this is almost always the case. So the previous example is barely used, and it's rarely used in real situations. Rather, this is the method. How do you find the degrees of freedom? The degrees of freedom that we find, here's an easy way out. Smaller of the two. One of them is N1 minus 1, one of them is N2 minus 1. This is in the case of unequal variances. You cannot assume the variance for one is identical to the variance to the other. We will look at that case also. But generally speaking, sigmas are missing. Generally speaking, we don't know anything about the variance. So this is the methodology that is used out there 99% of the time. As far as degrees of freedom is concerned, normally we use this one if we are doing it by hand. Technology, however, uses a different degrees of freedom because the degrees of freedom has a specific calculation that we don't have to worry about it in this course. Look at x1 bar minus x2 bar plus minus z. That is not changing. What is changing? E is changing. In the case of sigma missing for one sample, E was T alpha over 2 square root of S over N. Now it's S1 squared over N1 plus S2 squared over N2, which is similar to that. Test statistic, again, is similar to that. X1 bar minus X2 bar. And this goes to 0 because it comes from H0 over the square root of S1 squared over N1 plus S2 squared over N sub 2. And as far as the formulas are concerned, they are really similar with one sample. And using technology, instead of Z, we deal with the T. Z test becomes T test, and Z interval becomes T interval for 2. So 2 sample T test and 2 sample T interval. The only thing I want you to pay attention, when you go down the list, take a look at this one, number 6, pull, and we will look at that. That means when we are assuming equal variances, we are not going to assume that. So we always write no for this case. No, it's not pulled. So with that being the case, let's look at an example of that.
Listed below are stats for student course evaluation scores for courses taught by female professors and male professors. Females X bar sub 1 equals 3.8667, N1 is equal to 12, S1 is equal to 0.5630, males X bar 2 is equal to 3.9933, N2 is equal to 15, and S2 is equal to 0.3955. Use a 0.05 significance level to test the claim that the two samples are from populations with the same mean. Assume the populations are normally distributed.
So we have to write the given. It's really given to us symbolically. We don't have to worry about that. So we're going to start with the first step, H0 and H1. H0, as always, mu1 equals mu2. By the way, if you wrote mu1 minus mu2 equals 0, it has the same meaning, and that's absolutely fine. So mu1 equals mu2. So what are we testing? Test the claim that the two samples are from populations with the same mean. We are testing with the same mean. That means that is your claim. And it doesn't say less than or greater than, so not equality is the second part, which makes it a two-tailed test. So with that being the case, you need to calculate the test statistic. The top formula has it. And remember, I put that formula again, this goes to 0, you don't have to worry about it. Mu1 minus mu2, you don't have to write it. It comes from H0, that's why it's 0. So plug in, and it gives us negative 0.660. Now we need to do critical value. Comes from the choice of alpha and degrees of freedom. What is alpha? Alpha is 0.05. What is the degrees of freedom? Smaller of the two. N1 minus 1 is 11. N2 minus 1 is 14. Smaller of the two is 11. And it's a two-tailed test. And we look up the T-table. On the left column, you look for degrees of freedom, which is 11. For the very top area in two tails, because the two-tailed test is 0.05. And as you can see, negative 0.660. When you do the drawing for the critical values and you put the test statistic in between, that means it's not in a rejection region. Do not reject H0. So all we did, we came up with the part A, because that's all it does, our calculation. Part A. The calculation gives us part A of the decision making. Do not reject H0. And then what? Well, let's go back to step 1 and see what happens with the claim. If you're not rejecting H0, then you're not rejecting anything next to it, in which case is the claim. So that means the claim becomes true, and you do the rest.
A. Do not reject H0. B. The claim is true. C. There is sufficient evidence to support the claim that female professors and male professors have the same mean course evaluation score.
Now bear in mind, we want to look at the p-value and confidence interval in a moment. Take a look at the p-value here. 0.517, and it continues. This is larger than alpha of 0.05. Therefore, you don't reject H0. By the way, take a look at the degrees of freedom. Degrees of freedom is different than what we chose, and the reason is because of the calculation. They do the calculation of degrees of freedom to come up with that. It has an interesting calculation, A plus B quantity squared over A squared over N1 minus 1 plus B squared over N2 minus 1. What is A? S1 squared over N1. What is B? S2 squared over N2. It makes it more complicated. Can it be done? Yes, but it makes it more complicated. So with that being the case, if you use the technology, of course, you have the answer. and we're done here. Now, we want to look at the confidence interval. Remember, the numerator here can be used because when we do the confidence interval, we need that x1 bar minus x2 bar. When we calculate the E, we need this. So hopefully we've made a note of those to make life easier for the sake of calculation. So we are looking at the same question. We are repeating the same question, and we're going to go through process. So let's see what we get. So E has this formula, T alpha over 2. If you recall, it was 2.201 from the previous page. And then square root of S1 squared over N1 plus S2 squared over N2. The calculation ends up giving us the E of 0.42245. Now we're going to add and subtract, okay, so to x1 bar minus x2 bar. So x1 bar, so when you go through the process of calculation, x1 bar minus x2 bar plus minus E, it will result in this. And as you can see, the values go from negative to positive. That means 0 is there. That means do not reject H0. That gives you the same result.
The confidence interval limit does contain 0. Therefore, there is no significant difference between the two means. The confidence interval suggests that the value of 1 is the same as the value of mu2. So there is sufficient evidence to support the claim that female professors and male professors have the same mean course evaluation score.
Okay, so here's the p-value. T is negative 0.660. Degrees of freedom is 11. And the t-distribution table doesn't have it. So we end up with larger than 0.2. I will show you in a moment as to how we arrive at that using the table. And the technology, we already have the answer from the previous page. It was 0.517, and it continued indefinitely, 0.517 something. You get to the same result because it is larger than alpha of 0.05. P-value is larger than alpha of 0.05. Do not reject H0. Again, using the information, we have the answer. Look at the confidence interval if we do it by using technology. Why is that different? I'm going to emphasize that. I'm going to refresh your memory why it's different. The degrees of freedom we used was the smaller of the two, or 11. This is what we use. The degrees of freedom that they use, the technology uses a different degrees of freedom, 19.06. That's why we end up with different. Why is that? Because of the limitation of a table, because of the fact that it's hard to calculate that. I want to show you how the table works. If you're doing this by hand, you're saying the p-value is larger than 0.2. We don't have a definite answer, but we know for sure it's larger than 0.2, in which case, obviously, 0.2 is larger than alpha of 0.05. So the interpretation and the result will be the same as far as the p-value. But how do we arrive at that? Remember, the t is negative 0.660, and the degrees of freedom is 11. So let's look at the table here. Okay, so we are looking at the table. Let's say this is 11. Now, if you look at the numbers are getting smaller and smaller. So the number we were looking for was 0.66. Of course, it was negative, but it doesn't matter. So 0.66 is to the right of it. So take a look at area in two tails is 0.2 for the last given number of 1.363. So what is the area in two tails for the number we have as 0.66? I have no idea. But for sure, it's larger. Why is it larger? Because take a look. 0.01. It's getting larger as we go from left to right. So the t values become smaller, but the area in two tails getting larger. We are going to look at the third case, in which case, again, we are dealing with the independent SRS, large samples as we are dealing with normally distributed, or n is large, meaning n1 and n2 are larger than 10. Now, sigma 1 and sigma 2 are both missing, just like the previous one. We're going to use the t-test. What if we assume sigma 1 is equal to sigma 2 and pull the sample variances? If we go this route, then we have equal variances. Degrees of freedom is n1 minus 1 plus n2 minus 1, meaning they add up. In which case, look at the formulas that are different. if you look at what we have here, the denominator has changed. It was S1 squared over N1 plus S2 squared over N2 under the radical. And now it's S sub P, known as the pooled variance. So what is S sub P? This is S sub P. This formula is the same for the confidence interval, and as a result, this E will change. Take a look at the denominator here. You want to keep that, so it comes handy here. You want to use the numerator of that because you need it for x1 bar minus x2 bar. However, the strategy is we don't assume this. We're going to go with that if it says they have equal variances. So normally what? Sigma 1 and sigma 2 are missing. Normally, we don't know anything about the variances either, and therefore we don't assume equal variances. Here's another example.
Researchers conducted a study to determine whether magnets are effective in treating back pain. Reduction in pain level after magnet treatment. N1 equals 20, X bar 1 equals 0.49, S1 is equal to 0.96. Reduction in pain level after sham treatment. N2 equals 20, X bar 2 equals 0.44, S2 equals 1.4. A. Use a 6.05 significance level to test the claim that those treated with magnets have a greater reduction in pain than those given a sham treatment, similar to a placebo. B. Find a 90% confidence interval.
We've done this stuff, so I want to go through this fairly fast. The information is given symbolically, so we don't have to worry about that. Writing it out is not necessary because it's given in that form. Now, we have three possibilities. We use the Z or T with equal variances. As you can see, there's nothing about sigma 1 and sigma 2, so we cannot use the Z test. As far as the T is concerned, they don't say anything about assumption, so they should say assume equal variances to use the formulas of the previous page. Instead, there is nothing about that, so we use exactly what we did in the previous example. So let's go through the process. We want to find H0 and H1. Needless to say, H0 mu1 is equal to mu2, but let's look at H1 and how we write that. So let's read part A one more time. What are we doing? We are testing the claim that those treated with magnets have a greater reduction in pain. Right tail test, and that is the claim. Mu1 is larger than P. Again, I think I mentioned that. I want to mention it again. If you wrote mu1 minus mu2 is 0 and then mu1 minus mu2 is larger than 0, it has the same meaning. And the only thing is you want to be consistent. Either use mu1 equals mu2 along with mu1 larger than mu2 or the other one. Right? If you do either one is fine as long as you're consistent. Don't mix and match. Using the top formula, you want to find the test statistic. You plug in and it results in the following. After you do the math, you get the test statistic of 0.1320. Critical value comes from the choice of alpha. So you need the alpha is 0.05. Degrees of freedom is smaller of N1 minus 1 or N2 minus 1. It happened to be the same, so it's 19. So it is a right tail test, and this number is 1.729. So where is the number 0.1320? This number is somewhere here, 0.1320, which is way into the non-rejection region. Therefore, you do not reject H0. If you're not rejecting H0, in essence, you're rejecting H1, and therefore you're rejecting the claim, and therefore the claim becomes false.
Do not reject H0. The claim is false. There is evidence to support the claim that those treated with magnets have a greater reduction in pain than those given a sham treatment.
If we want to go with the p-value according to the graph here, then the p-value is the area to the right, the yellow shaded region, where the blue shaded region is alpha. So it's clearly larger than the alpha, and therefore the same decision is made. Do not reject H0. So find the p-value. It's a right tail test. The p-value is the area to the right of test statistic t equals 0.1320, and with the same degrees of freedom, by the way, 19, you look up the table, or something close to that. The table doesn't give you an answer because 0.1320 is not there. The same thing, it ends up being really larger than 0.2, if you will. But this is from technology, and so there you have it. This is the technology, and by the way, notice two things. This is the p-value, and degrees of freedom is not 19. Degrees of freedom is actually calculated, the formula that I mentioned. And so with that being the case, let's move on to the confidence interval. Confidence interval, you have to calculate the E. You have the same T, 1.729. Confidence interval of 90% correspond to 5% significance level of one tail. It doesn't matter left or right. Alpha was 0.05. If this is 0.05, you have to make this one also 0.05, and that's how you arrive at 90%. And therefore, it gives you the same T. Now, take a look at the denominator here that I put it in green on purpose. This one is what I'm using to show you how easy it is to do the calculation. I am saving time by using the old calculation. Now, x1 bar minus x2 bar. Take a look at up here. I need this one. Where does this come from? Look at the top of test statistic. And what is that equal to? 0.05. 0.05 plus minus 0.66. And we end up with this. So that's a fast and easy calculation. And it contains 0. So do not reject H0.
Researchers conducted a study to determine whether magnets are effective in treating back pain. Reduction in pain level after magnet treatment, N1 equals 20, X1 equals 0.49, S1 equals 0.96. Reduction in pain level after sham treatment, N2 equals 20, X2 equals 0.44, S2 equals 1.4. A. Use 0.05 significance level to test the claim that those treated with magnets have a greater reduction in pain than those given a sham treatment, similar to a placebo. B. Find a 90% confidence interval.
We are using the same question. What's the difference? We are assuming equal variances, and therefore we are using different formulas. So the first step is identical. I don't want to discuss that. We've seen it. We don't want to waste time. Now, the rest of them are slightly different. Number one, you have to calculate S sub P. So take a look at the formula here. We need to calculate this. This is the pooled variance. We go through the process. We come up with the answer. Granted, it takes a little bit of a time to calculate this, but it's really not too bad. You plug in the information into the formula, and you end up with S sub P being 1.4408. Now, by the way, because the sample size N1 and sample size N2 are identical, if you square S1 and square S2, it has to be squared. Add them up, divide by 2, you get to the same answer. Just because they have equal sample sizes. Otherwise, it's not the case. So now, again, because that's the case, when we calculate the test statistic going through the formula that is given on the right top, we end up with 0.1320. Again, I want to make sure everybody understands what's happening. This test statistic is identical to the test statistic of previous page. There is only one reason for that. N1 equals N2, otherwise they won't be the same. Because N1 equals to N2, they end up being the same. If they are not, you will have different answers. Now, the next one is critical value. How do we come up with the critical value? Well, we need a choice of alpha, which is the same as previous page, 0.05. And degrees of freedom, we said, in the case of equal variances, what do? We add them up with you. That becomes the degrees of freedom. That means N1 minus 1 plus N2 minus 1. So 20 minus 1 and 20 minus 1, they add up to 38. So degrees of freedom is 38. Alpha is 0.05. You're dealing with the right tail test is 1.686. So that is your answer as far as the test statistic is concerned. So 1.686. That's your critical value, my apology. And if the critical value is 1.686, You look at the location of test statistic when it comes to the graph. Clearly, this test statistic ends up being somewhere here. And that's way into the non-rejection region. You get to the same decision making. This is identical to the previous page, so we're not going to bother to read that. What matters is that do not reject H0 and write the rest of it. This corresponds to 90% confidence interval because one tail test alpha is 0.05, then 90% confidence interval. So we need to add the E to X1 bar minus X2 bar. This one we already have it from the previous page, was 0.05. Now, this is what we need. It's a different calculation. Hopefully we've made a note of that. And then we are putting the T here. We are multiplying by this value here with the asterisk. So 0.05 plus minus 0.64, you want to take it further with decimals. And so mu1 minus mu2 is between negative and positive value, which results in the same thing. 0 is contained. Therefore, you do not reject H0. And what happens here is that the confidence interval is slightly narrow as far as the steps involved and how we arrive at the answer. If we go using a calculator, take a look at the bottom. It says poll, and we said yes here. And that's the difference. So you really want to pay attention to this very last step, everybody here. One before the last time. And so with that being the case, we end up with the following as the answer. And as you can see, the p-value again, 0.44794. It's way larger than alpha 0.05. And again, take a look. If we were to use just this graph, go back to the graph. This is your area of interest, okay? The test statistic. For the area to the right of the test statistic. Next example.
A researcher hypothesizes that the average number of sports that colleges offer for males is greater than the average number of sports that colleges offer for females. A sample of the number of sports offered by colleges results in males x bar 1 equals 8.6 and 1 equals 50, and females x bar 2 equals 7.9 and 2 equals 50 at alpha equals 0.10. Is there enough evidence to support the claim? Assume sigma 1 and sigma 2 equal 3.3.
This one is also not used in real world because we don't know about sigma 1 and sigma 2. However, sometimes in some cases, based on the previous experiments or experiences, they know that. So assuming sigma 1 is equal to sigma 2, we use the Z test, 2 population Z test. With that being the case, what is given, everything is given symbolically. H0 mu1 equals mu2, but what is H1? Right tail test, and that is the claim. We use the top right formula and we plug in all the numbers that we said it's given, and we end up with test statistic of 1.06. Let's come up with the critical value. Critical value uses the alpha, which is 0.1, and we use the Z table. Gives us 1.285. Now graph this critical value and then locate the test statistic in respect to that. So we are going to locate that accordingly. And so with that being the case, we make a decision. So take a look at the location. As you can see, the test statistic is way into the non-rejection region. Do not reject H0. So when you don't reject H0, you go back to step 1 and you see what's happening with the claim. The claim becomes false, and there is not enough evidence to support the claim that colleges offer more sports for males than they do for females, according to this data. Finding the p-value is the area to the right of test statistic. Z equals 1.06, and it's 0.1446, which is way larger than the choice of alpha, which is 0.1. Therefore, we get to the same decision, which is do not reject H0. Finally, I want to show you the formulas. If you use the table, we use the simple and conservative estimate of n1 minus 1 and n2 minus 1, the smaller of the two. The technology uses the more accurate but more difficult estimate, meaning uses this one. You want to be aware of that. And as far as the p-value and critical values refer to the t-distribution table, the t-distribution table is extremely limited because they use the same formula. They basically, the p-value and the traditional method give us the same result, okay? So the p-value method, the critical value method, and confidence interval all use the same distribution and standard error, so they are all equivalent in the sense that they result in the same conclusion. Finally, take a look at this one. If sigma 1 and sigma 2 are known, the formula that you use for the standard error, the denominator, if you will, of your test statistic is this one. If that's not the case, and it's almost always the case, can you assume sigma 1 is equal to sigma 2? If yes, you go with this one. But if not, you go with this one. And this is the one that is almost always used. So let me repeat. Normally, sigma 1 and sigma 2 are both missing. We can't use the first case. Normally, we cannot assume sigma 1 is equal to sigma 2 unless they tell us somehow they are aware of that and they tell us. Therefore, most of the time, we use the case that uses the t-distribution and sigma 1 is not equal to sigma 2.